Since the natural gas liquid process is a high pressure process, then there will be no need to add a low pressure storage tank, but I will show you how to add a pressure safety valve, then a rupture disc in a later video. To add a pressure safety valve, click on Add PSV button as you can see here. Then move to the flowsheet area. Notice now that the cursor changed to the plus sign, and once you hover the mouse over any potential stream, for example this one here, a blue square will be shown toward the end of the candidate stream, where now you can click on the blue square to add a PSV. In our case, we will add a PSV to the compressor discharge line. This line contains liquid hydrocarbon gases recovered from the distilling column. So click on the blue square to add a PSV as depicted here. Next, we will customize the newly added PSV. From the Safety Analysis pane, click on PSV1 subfolder, and Equipment tab form will show up. Here you have the choice to enter the input data manually or by reference. To avoid yourself a headache, select the reference option and Aspen Plus will complete the job for you based on the latest simulation results. Next, click on Scenarios tab and then on Create Scenario button to create a new scenario for our PSV. Once you do this, the newly created scenario will show up. Select, then highlight the scenario, and Open Scenario button will become active. Click on it to edit the selected scenario. Here we can either define our own scenario via sticking to User Defined option or select from the drop-down menu, as you can see here, classified under different categories, as there are many possible scenarios to select from. Notice that Aspen Plus will notify you if further information is required by displaying a yellow strip at the bottom of the form with a text indicating the missing parameters. For example, in our case, Aspen Plus is asking us to select a reference stream in order to calculate the relief properties. Let's set that to the compressor discharge stream to which we connected the PSV. And then select the reference option for the relieving temperature, so that Aspen Plus can complete the data for us based on the last simulation results. Now back to our scenario type. Notice that we can create different scenarios for the same added PSV, as many as we wish, but I will discuss one scenario here. So I will select the abnormal flow through valve scenario. Then I will set the total back pressure to 1 bar. The reason for this will be explained further ahead. Notice now that Aspen Plus still requires some input data, namely the required relieving flow. That explains why a yellow strip at the bottom of the form persists until we enter the required input data. Consequently, we need to enter the relieving flow via selecting the reference option for the relieving flow method calculation, as you can see here. This will transform the yellow strip into green. Now, based on our input, Aspen Plus has calculated the required orifice area, estimated here at 0.7 square centimeter. At this stage, you can select the orifice area from the drop-down list that you can see here, or leave this until you reach the Rating tab. In my case, I will select the orifice area now and set that to 1.26 square centimeter. Notice here that if you select an area which is too small, for example this one here, or an area which is too large, for example this one here, then Aspen Plus will advise you to reconsider your choice via the yellow notification strip at the bottom of the form. Okay, now there is one more selection, that is determining the properties of the relieving phase itself as being liquid, vapor, mixture of both, or supercritical fluid. In our case, we will set that to vapor with the direct integration based on the homogeneous equilibrium method. The equations used with this option are based on the homogeneous equilibrium method, which assumes the fluid mixture behaves as a pseudo-single-phase fluid with a density that is the volume averaged density of the two phases. This method is based on the assumption that thermal and mechanical equilibrium exists as the two-phase fluid passes through the PSV. For high momentum discharges of two-phase systems in nozzles longer than 4 inches, both thermal and mechanical equilibrium can be assumed. These assumptions correspond to the homogeneous equilibrium flow model. This method can be used for all two-phase discharge scenarios, including supercritical fluids in condensing two-phase flow. When using this method, the Aspen Plus built-in properties calculator is used in order to evaluate fluid properties along the isentropic path. Now, after getting the green light, Aspen Plus will do some background calculations, and the results are shown both in Scenario Setup and Fluid Properties tab form. Here is a summary for terms appearing on this form. The maximum allowable BP that you can see here is the percentage of the set pressure allowed as back pressure for the valve. This value depends on the set pressure and the valve type considered. The total back pressure is the pressure at the outlet of the relieving device. It is the sum of the built-up back pressure and the superimposed back pressure, both constant and variable. There will be more about this further ahead. The relieving pressure is the pressure at the inlet of the relieving device. It is the sum of the set pressure and the allowable overpressure. Finally, the relieving temperature is the temperature of the relieving conditions at the inlet of the relieving device. The allowable overpressure percentage has a default value of 21% of the set pressure for fire emergency scenarios, and only 10% for all other scenarios. Let's take as an example our compressor discharge stream, to which we have connected the PSV. In our case, the operating pressure is 68.94 bar absolute, or 67.93 bar gauge. So the set pressure is 67.93 bar gauge. And since we selected a scenario that is not fire emergency scenario, then the allowable pressure is 10% of the set pressure. So 10% times 67.93 bar, which is equal to 6.79 bar, as you can see here. As a result, the relieving pressure, which is the sum of the set pressure and the allowable overpressure, is equal to 74.73. For the total back pressure value, you may edit the value under the Scenario Setup tab window, as you can see here, and an edit box will show up with the details on how such a value is calculated by Aspen Plus. Basically here, the total back pressure is the pressure at the outlet of the relieving device. This pressure is used to calculate the properties of the fluid at the exit of the relief device. It is the sum of the built-up back pressure and the superimposed back pressure, both constant and variable. Finally, the relieving temperature is set to the operating temperature of the compressor discharge, which is in our case here 128.5 degrees Celsius. Okay, let's now go to the third tab, that is PRD data. As you can see here, Aspen Plus has automatically filled in almost all the PSV characteristics based on our input data. You can see the PSV flange size and rating as recommended by Aspen Plus. Notice here that we don't have any warning regarding our PSV design and calculations, which means we're good. Basically, at this stage, you don't have a lot of things to do. You can rename the newly added PSV by clicking on the Edit here, or change the default setting for the PSV type and the PSV body material. In my case, I will stick with these settings. Now perhaps a comment here. Since our compressor discharge stream is at a high pressure of 68 bars, then I will choose HP flare for the discharge location. Okay, now move to the rating tab window, and here the orifice size specifications are checked. You may enter or adjust the orifice size specifications, which will be selected from a drop-down list as seen here. Notice that, as discussed previously, if you select an orifice size larger than needed, for example this one here, then you will end up with a yellow strip indicating that the required capacity is smaller than the rated capacity. The selected PSV is likely to chatter in this case. Consider selecting a smaller PSV or splitting the PSV in two or more smaller items. In principle, you can start small and grow up to the limit where you are prompted by the warning, or you may start big and shrink in size until you get the green strip. Notice here that the required capacity is 4,952 kilograms per hour, which is 55% of the PSV rated capacity of 8,863. Okay, now move to the last tab, line sizing. This tab pertains to the line sizing of the inlet and outlet pipe. Here we need to specify both the nominal diameter and schedule number for both inlet and outlet pipe. Here again we have to play tricks such that the selected nominal diameter does not end up with an undesired result. Specifically, at a very low nominal diameter value, we violate the pressure drop limitation on both inlet and outlet side of the PSV. So my advice to you, start simple and grow up in size until you get the green strip. For example, we can start by selecting 1 inch as nominal diameter and 40 as schedule for both inlet and outlet pipe. Then click on the button Run Line Sizing that you can see here to evaluate the piping pressure losses. As you can see here, with this first setting, we exceed the maximum pressure drop. Therefore, we need to try with a larger size.